Have you ever stopped to think about what's really running our modern world? I mean, behind the scenes of everything from your thermostat to a rocket launch, there's this hidden intelligence at work. We're talking about the silent brains behind the machine, and they're called control systems. Okay, let's make this real. Picture this. You're on the highway, you set your cruise control to, say, 70 miles per hour. It's all smooth sailing on a flat road, but then you start going up a hill. And yet, the car doesn't slow down. It just stays at 70. How? How does it know it needs to work harder? Well, that's not magic. It's an incredible engineering principle in action. And at its very core, the idea is actually wonderfully simple. A control system is all about one thing: taking a system, any system, and making it do exactly what we want it to do. It doesn't matter if the goal is a perfect temperature, a steady speed, or a super precise movement. The controller's job is to get it there, automatically. And here's the cool part. Once you know what you're looking for, you start to see that these systems are absolutely everywhere. I mean, they're the invisible backbone of almost all modern technology. The sheer variety of applications is just mind-blowing. We see it in the obvious places, right? The temperature control in your AC, the cruise control we just talked about. But it's also the unseen force guiding industrial robots, regulating our entire power grid, and it's even inside cutting-edge biomedical devices that are literally keeping people alive. And this idea isn't locked into just one field. It's a universal concept that pops up all over engineering. Take robotics, for instance. A really simple system might just send a fixed voltage to a motor and hope for the best. But a smart one? It uses something called PID control, a classic feedback trick, to constantly adjust on the fly. Same thing in networking. You could just blast data out at a constant rate, or you could use a protocol like TCP, which is smart enough to slow down when it senses the network is getting clogged up. You see? The core principle is the same. So what is it? What's the secret sauce that makes a simple system, well, smart? What gives it the ability to adapt and correct itself? It all boils down to one incredibly powerful idea: feedback. So let's look at the basic blueprint here. You've got an input, that's your goal, like I want to go 70 miles per hour. The controller then tells an actuator, in this case the engine, what to do. The actuator acts on the plant, the car itself, and that gives you an output, your actual speed. But here's the absolute key to the whole thing: the sensor. It measures that output and reports it right back to the controller. And that cycle right there is the famous feedback loop. Now let's ask the most important question of all. What if we just took that sensor away? What happens if the system is basically flying blind, with no way to measure its own performance, no way to check its own work? Well, that one question gets us to the biggest distinction in control systems. Over on the left, you have open-loop systems. No feedback. They just follow a command and hope for the best. Think of a cheap toaster. It runs for a set amount of time, whether your bread is frozen solid or already half toasted. It's simple, sure, but not very smart. Now on the right, you have closed-loop systems. They use feedback. They self-correct. That's your cruise control. Its sensor feels the car slowing down on the hill, and the controller immediately corrects for it. Yeah, it's more complex, but it's way more accurate and way more reliable. So how do engineers actually go about building one of these things? It's not just guesswork, not at all. It's a very structured process. Think of it like a clear roadmap that takes you from a problem to a perfect solution. Engineers really do follow a kind of journey to get there. This roadmap shows the three main phases they go through, and it's a logical progression from just understanding a system to being able to completely control how it behaves. Let's walk through it. It all starts with phase 1, system modeling. This is where engineers use the language of mathematics to build a model that perfectly describes the physics of the system. Then comes phase 2, system analysis. They take that math model and use it to predict how the system will act on its own. Is it stable? Is it fast? Is it sluggish? And only after they understand all that do they move to phase 3, control design. This is the creative part, where they build the actual brain, the controller, that will steer the system to do exactly what they want. And when you put all of that work together, well, that's when you get to the real purpose, the incredible power of control engineering. Ultimately, we're doing all this to achieve three big goals. First, to maintain a desired output. Engineers call this tracking. Second, to reject disturbances, like that big hill your car ran into. And third, to just fundamentally improve the system's performance, making it more accurate, faster, and way more stable than it could ever be on its own. So, after all that, what's the one thing you should remember? If you take away just one concept, let it be this: feedback. That's it.
the simple yet profound idea of a system measuring its own output to correct its own behavior. That is the engine driving all of modern automation. It's what turns a dumb machine into an intelligent one.
This ability to make our systems smart and adaptive has completely reshaped our world. And that leaves us with one last, pretty exciting question to chew on. Now that we have this incredible power, what's the next big, complex system we're going to teach how to behave?